So last time, so far we have arrived at the fact that the Navier-stokes equations, if you want to do it seriously, I mean you can solve Navier-stokes equations exactly for very simple problems, but for fairly reasonably complicated problems, you will not be able to solve it analytically or exactly. Here we want to solve it approximately, and we have two limits of Navier-stokes equations. The high Reynolds number limit, this is what type of equations? Anybody remembers the name? Anybody remembers the name? It's implicit. And who's the guy? That's Euler. Okay, so the viscous force and the viscous stress is 0. So you have the rho gu by dt equals, it's just balanced by the pressure forces. But remember, this is the total derivative that we discussed last time. So we have partial u, partial t local acceleration, and the measurable term, the cursor term, u dot nabla u, right? This is the nonlinear term that is responsible for the two many things: the turbulence, the lack of an analytical solution, the lack of even an existent solution to Navier-stokes, not to Euler. And it's nonlinear. So this assumption by itself to neglect the viscous stresses is not very helpful, because it's still the nonlinear terms are there. On the other hand, here we have the other limit. Reynolds number goes to 0. What's that limit? Nobody remembers the name? Stokes. It would have been cool actually if this is Navier-stokes, here is Navier-stokes, but you know, this is Euler. Stokes flow is linear, even if you write the unsteady version of it, but here is the steady version. Is simply the pressure forces balance the viscous forces. Okay? Simply. And luckily this is linear. That's great. But for airplanes, I mean, our main interest here, we are in the range of Reynolds number 10 to the power 7, 10 to the power 8. Okay, so tens of millions. We're really here. Viscous stresses may be really negligible, but the issue is that, like I said, this nonlinear term is still there, and this assumption by itself is not very useful to us to obtain analytical results and scrutinize our flow field. You can always go and solve numerically.
As well. So this only exists if it's steady, right?
Yeah, there is unsteady version here. You can add partial u, partial t, yeah, rho, if you like. Okay. Typically, people solve Stokes equations steady. Anyway, but you can always have unsteady version. Anyway, so here is the last time we spent quite a bit of time discussing and explaining vorticity, the rotationality of the local rotationality of the flow. Okay, any question about that? We have an example with a curved flow, local rotationality, curved flow without local rotationality, straight flow with local rotationality, all the combinations. So here is the brilliant assumption. Upon which every analytical theory in aerodynamics, whether steady or unsteady, is based upon which airplanes without which airplanes would not have flown in the early days, and of course this development would have been delayed so much. What's that brilliant assumption? You can see it here. So here is an airfoil at very large Reynolds number, so large Reynolds number, small angle of attack. Okay? Here is the flow field. Stagnation. We have boundary layer, and we learned last time that boundary layer really is a vertical layer inside which we have rotationality, we have omega vortices, right? We have vorticity. And the same thing here. And for high Reynolds number, these layers are really very thin layers. And then these guys will shed in the wake. And this is actually the difference in the vorticity in the boundary layer. Okay? These two layers, the boundary layer over the airfoil, and the wake, the shear layer in the wake. These, I mean, by very definition, they are vertical layers. But outside here, indeed, the vorticity is almost zero. Okay? This is very fair assumption outside of these two very thin layers. Okay? So this was the brilliant assumption. Why? Because it's very accurate. And second, it is enabling. Without it, we're still here. We have the nonlinear term. There is no hope to obtain an analytical solution. We barely made it for the existence of a solution by Marsden using very, very advanced mathematical tools. But other than that, we have nothing. But this assumption, we'll see today how enabling it is. It simply opens up the gate for analysis and analytical results, scrutinizing the flow field, everything. Why? Let's see why. So omega, by definition, omega is nabla cross u. Okay. Aside here, has nothing to do with fluid mechanics. This is pure math. When you have a vector field, A that is function of x. So field means it's a function of the space. And vector, it means that at any point it assigns a vector. So we have a vector that is function of the space. We call it a vector field in mathematics. A vector field, when it's curl free, so for a vector field A, if nabla cross A, if the curl of the vector field is 0, then we call it a conservative vector field. A is a conservative vector field, and more importantly than the name, the implication is that this vector field can be written as the gradient of a scalar function. So if we are in 3 dimensions, this vector field has 3 components. Each component is function of x, y, z. We're saying that each component is determined by the differentiation of the same scalar function along that direction. If you want A in the x direction, differentiate phi with respect to x. If you want A in the y direction, differentiate phi with respect to y. If you want A in the radial direction, differentiate phi with respect to the radial direction, with respect to r, and so on and so. Okay? So this is very convenient. Why? Because if A is unknown, which means 3 unknown components, now you reduce the number of unknowns to only 1 function instead of 3 components for A. Okay? And you have a very convenient way, coordinate free. You can write this in any coordinate system. You have a very convenient way of recovering A from the scalar function phi. And this is valid for any vector. Okay? Now applying it to our vector field in particular, U, the velocity field, because this assumption that the flow is irrotational, omega is 0, the curl is 0. So irrotational flow, that brilliant assumption, means that omega, which is nabla cross u is 0, implies right away that u can be determined as the gradient of a scalar function. Okay? Any questions about that? Okay, now in addition, we have that for incompressible flow, we know that the continuity, what's the continuity for an incompressible flow? Anybody remembers? What's the continuity? Anybody remember that? Simply nabla dot u. is equal to 0. So now if I substitute u as gradient of a scalar function, I immediately get Nabla squared of phi equals 0. This is our governing equation for incompressible irrotational flow. It's three-dimensional. I didn't make any assumption about the two-dimensionality of it, and more importantly, it's unsteady as well. I didn't make any assumption about whether the flow is steady or not. The only assumption is irrotational means that, incompressible here is the continuity, so this is the equation. So remember in the back of your head, this is always, it's simply continuity. Okay, this is just continuity, there is no momentum. Just the continuity gives you Nabla squared phi equals 0, and it's for 3D, unsteady, but here are the assumptions, it's irrotational and incompressible, okay? Which sometimes we refer as potential flow. Any question about that? Any question? On the other hand, let's see what this assumption of irrotational flow enabled. On the other hand, the incompressibility okay, 2D. So remember here, by the fact that the curl is 0, this immediately ensures the existence of a phi. We call it potential function. Okay. So just by assuming this or by having this fact, immediately ensures the existence of phi satisfies this equation. We have an analog for that. By the fact that the continuity is nabla.u is 0. The divergence of any vector field in 2 dimensions is 0. This ensures, so actually I should make like this. So incompressible means this is the continuity. Now this guy is 2D. This ensures the existence of a scalar function psi satisfying the following. You can always define, if it's in Cartesian coordinates where u, this is 2-dimensional, ui plus vj, you can always define it as u is partial psi partial y, and v is negative partial psi partial x. Now if you plug these here, it will be automatically satisfied. Okay? This equation will be automatically satisfied. The continuity will be automatically satisfied. It's as if you're getting any scalar function phi and defining your velocity field in this way from this scalar function. Now bring your velocity field and put it here. This equation will be automatically satisfied. Okay? Here is the other way around. Bring any function psi in the x and y and define your velocity field this way. Now you have u and v and go. Look at the continuity, it will be automatically satisfied. So psi automatically satisfy continuity, phi automatically satisfy the irrotationality. Okay? So now you have psi in this way. Let's go and look at nabla cross u. About that. What? So this, if the flow is irrotational, which is the assumption I'm adopting, this would be 0, okay? So now my flow is defined in this way. So let's look at this. So this is nabla cross u, so it's partial v partial x minus partial u partial y in the 2 dimensions. Okay, this is 2-dimension flow. So this is what? Partial v partial x, here v is a negative partial psi partial x, so this is negative psi xx. Negative partial u partial y, and u is partial psi partial y, so this is psi yy in the k direction. So this is negative nabla squared psi in the k direction. But this assumption is 0, right, for irrotational flow. So I have nabla squared psi also for an irrotational flow equals 0. Okay? So I have both. For an incompressible irrotational flow, I have n plus squared phi equals 0, n plus squared epsilon equals 0. Let us summarize these two things here. As always, anybody couldn't get these PDFs from the EEE Dropbox? There is a EEE Dropbox on which I post these. I convert them in PDF and I post them. So you should be able to see the syllabus and the last two lectures. And today I'll post the third and the homework. This is where you will find your homework. So let's summarize this. You don't have to write unless you know something that I don't write here. I say it and you like to have a note. Other than that, I'll give you these notes. So anyway, we have two things here. We have nabla cross u, this is omega, is 0, and we have the continuity. So this is assumption. Here we have a fact, the continuity, that nabla dot u continuity is 0. This is a fact. This is our brilliant, and I'm stressing the fact that it's brilliant assumption. Okay, so this guy automatically ensures the existence of psi such that u is psi y, v is negative psi x. Okay. Now, if you have them together, if you have this fact and this fact together, what do you get? For psi, I get n plus squared psi equals 0. This is 2 dimensions only. We have a stream function sometimes for 3-dimensional axisymmetric, and we have stream function for compressible flow. But you do it by construction. It's not, it's not natural like this. So natural stream functions for 2-dimensional flow. So what else? So this is n plus squared psi equals 0. We'll do it the other way around. So we'll get this guy automatically. So when I ask you what is the source of n plus squared psi equals 0, this is the assumption irrotationality. Okay. This automatically ensures the existence of a phi such that your velocity field is simply the gradient of it. And as you can see, this is coordinate free. You write it in Cartesian, polar, spherical. It's always like this. But over there, this is coordinate dependent. The definition of your velocity components on a psi is coordinate dependent. You have to tell me